Morning. I think the average speed.
Just a little bit more. I think they can see this.
Over the time range.
Oh.
So, over 36 or 15. That would be your speed.
I see, because I can kind of see what they're seeing in their body and their body.
That's crazy.
Oh my gosh.
Did you get the average speed?
Average speed.
I think it's just the distance you travel every time.
And at what section are?
I looked over his chapter. I actually have over one. The channel is awesome.
Channel's great.
Well, you see, I didn't like really read it. I was tired. I looked at it.
You'll like
So
it.
you get
Girl,
that's
from
great. I just want to make sure you would. I wanted to see why you're right.
Yeah, I talked. And she no, we.
Okay, yeah.
Why? Whatever. Probably said for a month.
So where are you guys going?
I know the guy runs it. There's something. Other kind of walk through maybe walk right like that. So I knew. Plus, that's very useful.
Yeah, when they get asked me to, and I'm like,
So that's okay.
okay, so that's it. Yeah, and then and I'm like, okay, let's talk. It's let's move around the stuff.
I emailed that guy, she
I do too, but
she's like, can you do this? And she has to ask her, she's trying to leverage her husband.
yeah.
So, but, what am I doing? I mean,
Who's my audience?
exactly. My student has no idea even how to start Excel, or is it, I said, I have some of my math classes. Introduced a little bit of Excel, meaning I'm assuming they know how to put stuff in Excel, that kind of stuff. And I'm showing them how to create a linear function, my function analysis built into Excel, something like that. But I'm not teaching them.
Well, that was it. I've done it. I know that. But my definition said you needed college.
Goes to read. Yeah, I've already talked to.
Well, I told myself,
You're doing the
But theirs is like a service trip, it's not.
no matter what, study I can teach you functional on hour and an hour and a half, an hour.
so they're doing it here and then
Well, I'm telling you.
the same place for their spring break trip this year.
That's weird.
Well, it's gonna be awkward because I'm going with the college. It's gonna be so awkward if I run into them.
College trip is gonna be much better,
Yeah.
mainly because it's not service, you're not expected to do anything except travel.
And I don't know. I just feel like this is a free route thing. I don't think it's gonna run as smoothly as
That's going behind the scenes, that's not.
college. The college seems very organized with all their trips.
If the statistics
I'm
involved,
excited.
we can maybe kind of swing that for that. We have.
Mainly, I mean, it's a lot of travel, but all of the places you go,
Yeah, absolutely, I would do the same thing.
and with the Costa Rica trip with them, you're just in one place,
Oh,
right?
yeah, it's our life.
Or those the
But I mean, that's just to me. That's not really learning about a culture. They want to play. You gotta like.
Well, I mean, that would not be
I just think that's really benefit about the study abroad and how early college kids have the opportunity to do it through the college.
Why are you so upset about that?
It's because of Sammy.
Oh,
But Sammy wanted to go on a trip.
Italy trip, but it's over graduation.
Just a
She got really
trigger.
upset with me about
I
that.
don't know.
You got anything next?
She was like,
It's not.
my next year is really not going to my graduation. She told me she's gonna talk my parents into making me go. My mom didn't go to his graduation. Dad didn't go to his college graduation. Neither one of them cared. They were just like, and I told her that. They were like, it's up to Sammy what she does. And then
To capture the flow of the arts.
she later apologized for her behavior. But
I think that
it's just
counts.
like,
When we walk in, what does it say? So the temperatures and get what they're saying. It's not.
it's just
It is updated.
Ew.
but
That's not,
Fun.
that's,
Right?
okay.
Dude.
I want to travel.
It's like
So we do Ireland next year, Brittany?
the facilities, but I mean, it's.
I got invited to a
I
10-day
can't-
trip to China.
Really?
Spring break
Yeah.
would match up, which
Where?
it probably
It's so
won't.
expensive.
So, you going?
I need someone to come with me. See, I went to Ireland and I was the only person from our early college.
I
that
mean,
went. There was
if I
one
go to
other girl from an early
States,
college.
States,
She went to Davis.
Yeah, well, yeah, that's
I tried to kind of.
With houses.
Ireland is a trip they do every single year.
Wake is only like second banana to NYU in terms of tuition. I can't believe
I didn't want to go where it's such a big culture shock when it's still in the middle of the semester.
level. So I'll reach out to him and see if there's.
I will give myself like a week of sushi. Come on.
It used to be, call me if you guys.
He never said anything while we got back home. So
Wait, who?
I want,
Hey, how long did it take you to do the residency stuff for your college out?
I stopped in the middle to get my parents' information. So if you have your
Well, if
parents'
I have my
information,
parents with me.
it doesn't. It's just a bunch of questions, but they're fairly quick.
Yeah, I'm glad we could do all this stuff.
you own a car.
But Facebook is last year.
Because they ask, I think they prepare for parents who are divorced, but they go ahead and ask the same question
Not the button,
when they
the-
file.
That was harder to do.
do you want to do that?
Is it
What is
fine?
it? Wait, what would you do?
I just press the button and then just leave it
Yeah,
on.
and we had to sign consent. We weren't allowed to post to Facebook. We were they
You
competition.
can ask him the question. Seinfeld question. I got 5 minutes.
Sure, go.
Oh, is it muted?
No, it's not. It's unmuted.
Oh, sweet. Mr. Gaddis.
You can't really see him.
As long as I
Yell
get.
it. Yeah.
Should I press the button?
Yes.
Mr. Gaddis, I have a question. Do you like that sitcom
That's what they're
Seinfeld?
saying.
Hang on a second.
If you like Seinfeld.
My face is in this side.
I'm sorry, say again, Reza.
Do you like Seinfeld?
I do.
Who's your favorite
Yeah.
character?
Wait, did you say yes? Yeah.
Kramer.
Oh, that's a good choice.
Yeah, he's got the
Mine
Kramer
was
hair.
Elaine.
You know, in a lot of the back the scenes or behind the scenes things or whatever, Kramer got so mad whenever they broke character. Because, like, Jerry basically had to be himself. And George and Elaine were just exaggerated. But Kramer had to play a character, so he was so mad. It was so funny.
Hey, Amanda,
Yes.
did you get a chance to email the extra credit?
Yes, I just noticed it this morning. I emailed it to you.
Okay, I hadn't seen it. I didn't.
Sorry about that.
That's fine. Pretty isn't good. To be honest with you, I forgot to grade the ones from here too, so it's all good. I forgot, we all forgot.
I try. I love Miami. You like fun.
Let's check. Well, we got to get going here. We got a lot to do. A lot of territory to cover today. Focus on that board still. Okay, good.
Okay, yeah,
While
fine.
I'm taking roll, so I'm just going to take roll real quick. We have the camera focused on. I listed on the board here the rules we've already covered and put some rules up we're going to cover today. Again, you don't have to copy them all down. They're in the book. They're also on a sheet on Moodle that I've posted on Moodle. But that's where we're headed today. I'm taking roll so you know where we're going.
Roll call. It's a shame Mason's gonna miss out on this.
He's not coming.
No. He's already.
Is Josh coming?
Is Mason here? Is that his book bag?
No, he's not here. That's Brittany Tate's book bag.
Okay, well, that's fine. I just
He's
wanted
the one that emailed you, Dale.
Mason would be like, Mr.
Oh, that's right. He did email me. That's right. Good.
My dearest Mr. Gaddis, I will depart from class today.
Okay.
Warm regards.
And hopefully you're not trying to copy that whole list because we've already covered most of it. The stuff we're going to cover today is at the bottom of the list. And so we need to get started. I apologize you're not going to be able to keep copying because we need to get going. We're going to cover what's called the chain rule. This is the newest, and it's the last of the general function rules. We've covered multiple sum, product, push. We did that. Now we're going to do the chain rule. This will be the last general function rule we cover. Then we'll be adding more specific function rules here in a moment. But we're going to cover the chain rule, and we're going to start this way. So suppose use 200 widgets per month, and earn $30 profit per widget. So, questions. What is the rate of change of profit per per widget. Okay. W, change in profit per widget to $30. Y'all agree with that? What is the change in widgets per month? Well, using similar notation, what would my rate of change of widgets per month look like in using similar type notation? W over DT or D month or something. We'll do T, that's fine, whatever. T is equal to 200. Okay, good. So if I now ask you, what is the rate of change of profit per time? So rate of change of profit per time. What would you think you should do to get that answer? That would be profit per widget times widgets per time.
Can you slide the camera over?
To the right, maybe?
Thank you.
Got that? Okay, profit per widget we said was $30, and the widgets per time is 200. So that would be $6,000 per month. We follow that line of thinking there. So in some sense, it almost looks like my DW is canceled out. I've got DP over DT, which is the rate of change of profit per time. I got the rate of change of profit per widget and the rate of change of widgets per time. It almost looks like the DW is canceled. Don't say they cancel because, we don't actually say that, because this symbol, derivative of P with respect to time, it's a singular symbol. It's not a division. It's just a name. So I can't really cancel those DWs, but in effect, it looks like I did in some sense. But that's going to lead us to what's called the chain rule. In fact, that is the chain rule right there. This is the Leibniz form of the chain rule. And we write that more generically. Instead of just in these letters here, in generic letters, I would say something like derivative of y with respect to x is equal to the derivative of y with respect to some other variable, we'll call it u, times the derivative of that other variable with respect to x. So any variable y and x, if you're going to find the derivative of y with respect to x, you can also do an intervening variable in the process, like we just saw here, and take the product of those two derivatives. Does that make sense? Now, that's in Leibniz notation, so using this derivative type of notation, dy over dx. But in the Gauss notation, we write it differently. So in Gauss, we would say that the derivative with respect to x of f of g of x is equal to the derivative of f, keeping g of x constant, times the derivative of g. Now, to see this notation, to understand this a little better, let me go back over what we just did here. And what I'm seeing is that price is a function of widgets, and widgets is a function of time. So I could back up here and say that I'm doing the price of the widgets at time. So if I back up to that, then my derivative is going to be derivative of price, keeping the widget idea constant, and then times the derivative of widgets with respect to time. And this still is going to be the same computation. It's still going to be 30 times 200. Okay? That's the chain rule. We'll do some examples of how we apply that. The foundation is understanding that you can multiply rates of change to get the overall rate of change. And so I'll write it right here on this board. What I just wrote over there, the answer is, I'll put it in red, so keep it separate so my second class I don't have to erase everything. So this is derivative of f times the derivative of g with respect to x. Or in Leibniz, as I said, this is dy by dx equals dy by mu times du by dx. So that's called the chain rule. Let's practice it a little bit with an example other than this one. We'll do just a generic function. So I'm going to give you a function f of x equals the square root of squared plus 3. Now I'm going to want to find the derivative of this function. So this is the derivative with respect to x of the square root of x squared plus 3. So the first thing I'm going to do is rewrite square root as an exponent so that I can apply certain rules that I'm familiar with. Now comes the thinking part. All I've done is given you a function, and I've rewritten it so that I can apply some of the properties we've already learned. But I need to see this function as a composition, f of g of x. So I want to see this as a composition, and since I call this f, this is going to be g of h of x. So let's identify. Can you give me a g of x and an h of x so that g of h of x is equal to f of x? But f of x equal to g of h of x. G of x will be x to the 1/2. I agree. H of x to x squared plus 3. We all see this? Okay, with that in mind, I'm going to change my my variable in here so that it doesn't look like x. I'm going to say, let's say g of u. Now,
Do you want h of u?
pardon me? I just made it g of u because I felt like having a different variable than x. I still get f of x is equal to h of x, because if I plug h of x into my g of u function, I get a function of x. Now, what is derivative of g with respect to u?
Oh, I see.
1/2 u to the negative 1/2. That's correct. Good. Everyone knows that quickly. Apply the power rule. You should be getting to the stage where you can quickly apply the power rule in your head. You all see this?
Mm-hmm.
Okay. What is the derivative of h with respect to x? It's just 2x, right? Because what properties did you apply there? Just a reminder.
The constant rule and the exponent power rule.
The constant and power rule after you applied what first?
The sum
Sum rule. So that's one thing I want to mention to you folks. As we go forward with derivatives, you need to be thinking this way. When you're doing, quote, doing derivatives, you're doing them in reverse order of operation. Stop and think about that. On this function right here, what was the last operation that you perform on this function? The plus was the last operation according to order of operations, right? When you do the derivatives, what's the first thing you do? You do the sum rule. Okay?
Dang.
So I like to describe doing derivatives like peeling an onion. You take an onion, you've got layers. You start on the outside layer, the last order of operation. That's the first thing you do when you work with derivatives. You keep going inside the onion by peeling back layer at a time in reverse order of operation. Okay, now let's see if we can put all this together. So, in my game that I'm trying to analyze here, u, the u right here, this is my u. Do you see this is u right here?
This is you.
I've got u to the 1/2. Right?
Yeah. Wait a second.
So, according to what I've just written,
Yeah.
the derivative of u to the 1/2 is 1/2 u to the negative 1/2.
Mm-hmm.
So I'm going to write that down. 1/2 u to the negative 1/2. And then by the chain rule, it's times the derivative of h with respect to x, which is 2x.
Nice.
This, what I just did here, folks, this was the chain rule. I multiplied the derivative of g function, which is the outside operation, the 1/2 power. I multiplied that derivative times the other derivative, which is the derivative of the inside stuff, this u thing that I'm talking about. And then I can just replace what u is defined to be. U is this x squared plus 3. So we'll just say this is 1/2 of x squared plus 3 to the negative 1/2 times 2x. I would simplify a little bit. The 1/2 and the 2 cancel, and so I just get x over the square root of x squared plus 3.
Hmm.
Now, it might have been a little clear, and I'll go back and change my notation slightly. I changed the input of g to be u. So if I went back here and changed h to have the name u, that may make more sense to you as well. My u, like I said, my u of x right here is x squared plus 3. Derivative of that is 2x. And then my g function is the outer function, which is the 1/2 power. So that's fairly straight up. Let's try a couple more examples real quick. Let's find the derivative of
So C sharp is exactly what it wants to do.
That's C# for programming thing?
It's a programming language.
Yeah, that one.
Okay, so I see a function here again. I could do this problem in one of two ways. Method one is what we've done in the past. We could expand out this binomial using the binomial theorem that we discussed previously. And that's a 5th power. And then you can apply the sum rule and the power rules and get the answer. Or, now that I understand the chain rule, or I'm trying to understand it, I can apply the chain rule here. Because in this game, I can see the inside function as being my u of x. And the outside function is g of u. So I'm saying here that g of u is equal to u to the 5th power. And u of x is equal to 3 minus 4x. From that, you should be able to easily do derivative. And folks, as we get more practice on this, I'm not going to be writing all of that down every time. I'm going to do a lot of it in my head for now. So what is the derivative of g with respect to u?
5u to the 4th.
5u to the 4th. Okay? And what is the derivative of u with respect to x?
-4. Is that it?
Simply -4, because it's a linear function.
Yeah.
So now I just have to put that information over here using the chain rule. Chain rule says I'm going to get 5 times u to the 4 and then times the derivative of u, which is -4. The u of x was 3 minus 4x. So this becomes, if I simplify, -20 times 3 minus 4x. And once again, this step right here was the chain. Feel like we're starting to get a little bit of a grasp on this. Let me let you try one yourself now for a moment, and then we can try something else. Let's see. So try that one for a moment on your note sheet. See if you can come up with an answer. Sorry, Lee's question?
Is that 2/3 or 2/5?
I wrote 2/3. I see that it does sort of look like a fifth. So let me make that look a little bigger and better. 2. Get better now? Zoom in a little bit. Thank you. I don't know if you can still see that. She's stepped out. Hopefully you've had a chance to work on it. Let me just talk about it for a minute. So just so you get you started, this time I did not write out G of U and U of X, all that stuff. If you want to, that's still fine. I'm showing you a little different strategy of handling these problems that I don't have to write all that out. So again, when I look at this onion, I see an outer function raised to the 2/3 power, and I see an inner function in here. So I'm going to do, in kind of a reverse order of operations, I do the derivative of the outside part first. So that uses the power rule, brings down the 2/3, makes it a multiplier, reduces the 2/3 to a power of -1/3. But notice, I did not change this in here at all. This is still U of X. Here. Over here, I'm now, by the chain rule, going to do the derivative of U. So I do not do the derivative of U inside of here. That remains fixed. And then I do the derivative of U out here, multiply. So I'm multiplying two different derivatives, like we saw in the beginning, together. Once you've done the derivative of the inside part out here, that's fairly simple. That's just a sum rule, a power rule, and so on. You ought to be able to do that one fairly quickly in your head. And then I just simplify a little bit. Multiply the 2 and this together, put this negative exponent to the bottom. Questions on that? You could do multiple levels of chain rule as well, instead of just, this is 2 levels. How would you handle, real quickly, and then we got to try something else. How would you handle something like this? Let me think, how am I going to do this? How about square root of x squared minus 1 over x squared, all raised to the 1/3 power. Then it gets a little bit more complicated. We should try one like this. Talk our way through it. In terms of reverse order of algebraic operation, what is the last operation you perform, I wasn't doing derivatives and you just had to evaluate that expression, what would be the last operation you would do?
That exponent. No.
1/3 power would be the last thing you do, right? Because that's outside the parentheses. Inside the parentheses first. So in terms of derivatives, that will be the first thing I do.
Yeah.
So this gives me third of, don't do anything on the inside yet.
Okay.
So negative 2/3 power times chain rule. I have to do the derivative of the inside. All of that? I did the derivative of the outside function, if you will. Now I'm going to do the derivative of the inside function. But what does that entail? What is the last operation you would perform on that? If that was my only function, what would be the last operation you perform algebraically?
Would be the division.
Yes. So what rule are you going to use?
The quotient rule.
Good.
Oh my gosh.
Times quotient rule. Quotient rule requires me to do the derivative
Oh my god.
of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. Oh, wait, there's more. Well, now we'll double the order.
He looks like
Oh.
a guy. Sam, wow, that's double model over there.
Okay. Now I got to focus on doing the derivative of these pieces inside the quotient rule. I've got two derivatives I still have to do that are inside the quotient rule. Okay, so I got to focus on this first one. Derivative of the square root of x squared minus 1. How are we going to handle that?
Are we gonna have to do another chain?
We have to do another chain rule.
A chain?
This would be x squared minus 1 to the 1/2 power. You've got to do a chain rule on that one.
Dadgummit.
You see that? My point is that this can quickly get the question flowing.
On the denominator, shouldn't it be x to the 4th?
That's what I was thinking.
Yes, thank you. Good catch. X to the 4th. Good catch. Thank you. Thank you. Okay, so how do I do the derivative of this now? This x squared minus 1 raises, so we're going to do a chain rule. So what is that chain rule going to look like as my derivative? Right, so?
Times 2x.
Are you talking about like you set it up?
I want you to tell me what the answer is.
Answer. Well,
Well, it's 1/2.
1/2 to the x squared minus 1 to the negative 1/2
Yes?
times
No.
the derivative. Is that right?
Derivative of this inside stuff. What is the derivative of this inside stuff?
You're gonna say it's 2x?
And then we still got a times x squared right there.
Oh my gosh.
Minus, I'm going to rewrite that as x squared minus 1 to the 1/2 times the derivative of x squared is 2x. Wow.
Wowie.
I guess for now we'll let you stop there. There's a good bit of cleanup that could be done on that, but we'll let you stop there for now.
I think it's
Algebraically, I've got some negative exponents I can deal with and so on, but we'll stop there. Point was that so all this is you can repeatedly apply various of our rules. The key is always be thinking, what is the last operation I performed algebraically, and that will be the next derivative that you do in terms of which rule to apply. Okay, so that's chain rule. You have some homework in section 2.4 on that. One more thing I need to do is you apply the chain rule for some what's called implicit differentiation. So we need to talk about implicit. We're still going to do some specific function rules over there. Okay, so everything we've been talking about tonight, up to date, in terms of derivatives, have been derivatives of explicit functions. So all of that board over there is derivatives of f of x, i.e. explicit functions of x. But what about equations that are not functions of x?
Oh, you're talking about like a circle?
A circle. So as an example, as a set of circle, let's talk about this circle. Perfectly good circle. You learn about it in great detail in trigonometry.
Mm-hmm.
Circle. It's a wonderful little thing. But that circle is not a function of x. But what if I wanted to know about the tangent to this circle at some point? If I wanted to know the slope of the tangent at that point, that might be important to me. The problem is, everything I've learned is dealing with derivatives of functions, but that's not a function. So how do I do the derivative of it in order to find the slope of the tangent? That's what we're going to do, called implicit differentiation. So implicit differentiation, you assume y is an implicit function of x, i.e. y of x, and use the chain rule.
Mr. Gaddis,
Yes?
what is
Question?
implicit?
Implicit is the opposite of explicit.
So not obviously there.
So like explicit, it means like before your very eyes. You can't miss it because it says f of x. So it's explicit is before your eyes. Implicit is not before your eyes. It's implied. Does that make more sense?
Yeah.
Implicit is the opposite of explicit.
Yeah.
Okay, so what I'm going to do is I'm going to do the derivative of x squared plus y squared equals 1. Here's how. I'm going to go over here on this board. I've got x squared plus y squared equals 1. I'm going to apply the derivative back to x on both sides of the equation. So far, so good?
Mm-hmm.
On the right-hand side, what's the derivative of 1?
0.
On the left-hand side, I'm going to apply the sum rule. So I get the derivative of x squared plus the derivative with respect to x of y squared. So that was the sum rule. What's the derivative of x squared with respect to x?
X.
Here's where we have to be careful, folks. Since this is not an x variable, in some regard you think of it as being constant with respect to x. But we are assuming that it's an implied function of x. So what we're going to do is think of this y function as being an inner function, like f of g of x. So think of y squared as some function y of x squared. Are we understanding what I'm saying there? So it's not just variable y. Think of it as a function squared. So you're going to do the chain rule on it. So the chain rule means I'm going to do 2 times y, 2 times y, times the derivative of the inner function, which is y. Oh, see, that's the chain rule. This is a chain. If you view y as a function of x, then the derivative of this is the derivative of the outside, which is 2 times the y, times the derivative of the inside. That's what I've written. 2 times y times the derivative of the inside. Are we clear on this now? Can you follow?
Yeah.
Like we did a moment ago. When we had a parentheses with a square on the outside, we did the derivative of the outside power, and then the derivative of the inside stuff. My inside stuff is just called y. Well, let's keep going. What is the derivative of y with respect to x?
Is it 1?
Y by dx.
Oh, y by dx.
Y prime of x, yeah, see 1.
Wait, so was it right?
You can write y prime if you'd like, or you can write dy by dx, either one. Now, can you solve for dy by dx from this equation? Yes. Dy by dx equals negative 2x over 2y, which is negative x over y.
Yeah.
Yes? So, for example, go back over here to this circle. Suppose that was 60 degrees on my unit circle. What ordered pair on the unit circle is located at the end of a radius at 60 degrees? What ordered pair does that represent?
1/2.
1/2 and
Root
Root 3 over 2.
root 2. Excellent. That's right. Okay, according to that we just created, the slope of my tangent
My gosh.
at that point is equal to the change in y over change in x, derivative of y with respect to x, which we just said is negative x over negative y on this unit circle. Not always, just that unit circle. But at that particular location, the x value is 1/2, and the y value is root 3 over 2. You invert and multiply, you get negative 1 over root 3. or root 3 over 3 if you want. Okay, so that's implicit. You can do that with any equation, even if it's not an explicit function. Now, in order to, let me see what my time is. I need to do some more. I'll come back to another example of implicit in a little bit. I want to finish out, because we're not going to meet tomorrow. I won't see you again until Monday. And we spent all day yesterday doing some homework. I'm going to hammer through these last couple right here. So let's start. I'll leave this on there for now. Let's go over here.
Is that the same as negative root 3 over 3?
Okay, exponential derivative. So what I'm now going to do, understand the derivative of an exponential function. In particular, I'm going to start with e to the x. E to the x. Exponential is different from power because that means the variable is in the exponent and the constant is in the base. The other way around, with power, those roles are reversed. But exponential, we have a variable in the exponent and a constant in the base. The answer is not the same rule. It's not x times e. It's not x times e to the x minus 1. That's not the correct rule. Okay? It doesn't apply. That's the first guess most students make. They think, oh, well, they'll just apply the power rule and make this pointing out. This is not the case. Not the case. This is x times e to the x minus 1. That's not true. It's a different game altogether now. So, what does it mean? Well, let's try the definition since we're not sure. What does the definition of derivative mean? Or how do you state the definition? H goes to 0. E to the, I got to plug an x plus h in here. Y'all remember that? Then we got to plug an x in there. And we have to divide by h. Okay. Now I'm going to do a little bit of algebra. By rules of exponents, this can be rewritten as e to the x times e to the h. Read. E to the x times e to the h makes e to the x plus h.
Yeah.
Now, by algebra, I can factor out an e to the x. Right?
It's not a definition, it's not a,
Yes, that's a theorem inside the parentheses. That's exactly right. Good observation.
Oh,
I'm going to
I
split this.
don't think Davidson heard that.
Okay, Davidson, the suggestion from Jacob was he observed that these parentheses over here, that's something we've seen before. And it was defined in a theorem back in page 120 something. It was defined, and we'll do that. I'm going to split this up by the product of limits can be handled by splitting them across the product. And as Jacob observed, this is something we learned before, back when we were studying limits. That number turns out to be 1. Good observation, Jacob. Now, what about the limit h goes to 0 of e to the x? Well, h is changing, but there's no h there. So it's not affecting it any. So it's just e to the x. And e to the x times 1 is just e to the x. Now, stop and let your brain wrap around what we just figured out, folks.
Wait, oh my gosh.
Derivative of e to the x is e to the x.
Well, I mean, that makes sense.
That's one big reason we call it the natural base.
Oh.
Okay? It's the only function in the world, whose derivative is equal to itself. Only one. Graphically, what does that mean to you? The slopes of the tangent line on e to the x create e to the x. E to the x is like this. I equals e to the x. If you map the tangent lines, this is a very small tangent line. That's a little more. That's one tangent line. That's a little more, a little more. So if you graph those, you get the same picture as you started with. That's what that says.
Wonderful.
Okay? Cool. Cool is right. Chain rule can be applied to that. How do I apply the chain rule real quick? We got to do the others. So, how would you do the derivative with respect to x of e to the x squared plus 3x? Well, according to the rule we just learned, the derivative of e to the something is e to the something.
Yeah.
But this time, the something is not just simply x, so I have to apply the chain rule.
Oh my gosh.
This, do y'all see this? This is the chain rule. One more time. If you were doing order of operations algebraically, what would be the last thing you'd do? You would first do x squared plus 3x, and then you would apply that as an exponent on e. So the last thing you did was that exponent on e. Well, e to the exponent is just e to the exponent. But the inside stuff has to still be derivatized. That's not a real word, I just made that up. Derivatized, and we do that with a chain rule. And then we're almost done. Okay, so now I'm done. We follow that? So e is a really nice function in that the derivative is very simple, but it can get more complicated because you can apply the chain rule. Okay? So be careful on that. You'll see some homework where you got to apply the chain rule on e. But the derivative of e to the x is the only function in the world that has itself as its derivative. But what about other bases? How does that work? So let me write my answer over here. This was e to the x. Now we're going to do other bases. What about b to the x? So I want to figure out the derivative of b to the x. So that's a different base. That's not base e. Base e is the only one called the natural base. Other bases are just called bases. So how do I handle the natural, the non-natural bases? I'm going to handle it by converting. I'll agree. You have to recognize from properties of exponents that e to the logarithm of b is equal to b.
Yeah.
Recognize that? So therefore, I can replace this b with e to the log of b. So this becomes derivative of e to the log of b all raised to the x power. Okay, so this is the derivative. And by exponent properties, I can make this as e to the x times log of b right? Power on the power you can multiply from create calculus.
Yeah.
Okay. So now this is an e to a power. That's a variable power, not a constant power. So according to the property we just learned, this is e to x times ln b times, but be careful. The inside is not simply x. I have to apply the chain rule. So I have e to the x ln b times, what is the derivative of x times ln b? Well, ln of b is just a constant number, folks. It's like 7. So what's the derivative of 7x?
7. Is it just L and B?
Yeah, so it's just ln b. Y'all follow that?
Sure.
Okay. Almost done. We just need to rewrite e to the x ln of b right here. All the back up. E to the x ln of b came from e to the ln of b raised to the x, which came from b to the x. Agreed?
Yeah.
This thing right here just becomes x times ln of b. And there's my derivative of b to the x. X times ln b. Quick example. With respect to x of 3 to the x squared plus 4x. According to the property we just learned, the derivative, whenever you have an exponential function, the derivative involves just the same thing again. But if it's not base e, then you got to multiply by ln of the base. This becomes 3 to the x squared plus 4x times ln of 3. But what else do you have to take into account this time, folks? That's like a function inside of a function again.
Composition.
Just did with g, we got to do the chain rule. So you're going to do the derivative of x squared plus 4x. So that was, I have to do a chain rule there. So this part, the first part right here, is just the formula we just created for a base b. But it's not just x, so I can do a chain rule on it. So the final answer comes out to 3 to the x squared plus 4x times log of 3 times 2x plus 4. Okay. Assignments. Good. I can do the last one real quick. Okay, so that's exponential. They are fairly simple, but you got to practice. You've got some homework to practice on. And they can get, as you can see, fairly complicated, fairly quick by if you include the chain rule in there. So be aware of the chain rule and be able to do these exponentials. The last two we got to do are the inverse of the exponentials. Go back over here. I'm trying to figure out the derivative with respect to x of the natural log of x. Now, instead of trying to use the definition like I did a moment ago, I'm going to change games this time. I'm going to, okay, let's start off with y equals the log of x. I'm just going to choose to call it y equals log of x. But what does that mean by definition of logarithm? Not definition of derivative, definition of logarithm. E to the y equals x is what that means by definition of logarithm. That is correct. So this is definition of natural log. Good, good, good. Now, I can apply the derivative to both sides of the equation and do implicit differentiation. I'm going to do implicit. I'm going to apply the derivative to both sides of my equation. And be careful again. The right-hand side is easy. The derivative of x with respect to x is just 1. By now, we can do that quick and easy. We all see that's just 1. But what about the derivative with respect to x of e to the y, where y is an implicit function of x? So the derivative of e to anything is e to anything. But since that's not simply an x, then it's times chain rule, the derivative with respect to x of the inside function. Chain rule. Y'all see a chain rule there?
Yes.
You have to view y as function of x. And it's an implicit function of x. So it's an inside function to the e function. And the derivative with respect to x of y is just dy by dx. So dy by dx equals 1 over e to the y. So far, so good?
Mm-hmm.
I'm almost done. I wanted to find the derivative. I found a derivative. But it says it's e to the y. But I wanted it in terms of x, because I started in terms of x way back at the top. So how can I convert this to be in terms of x? What does it say e to the y is equal to?
X.
So the derivative of ln of x is 1 over x.
Is that the logarithmic specific function rule?
Yeah, that's the specific functional rule for natural log. 1 over x. How much shall we get now? 5? 4 minutes. Okay, well, let's do the, real quickly, an example of this, and then we will just kind of state what the other one is, because the other one is very similar. Like in exponential, there was a relationship between the two. Logarithmic, there'll be a relationship between the two, clearly. Let's do a quick example. Derivative with respect to x of the natural log of 3x to the 4th plus 7x. See if you can take a minute without me telling you what to do. See if you can apply the rule we just learned and what we've been talking about all day. See if you can come up with a derivative of that. That's and rule. The key, once again, is I see an inside function, so I have to do a chain rule. So this becomes 12x to the third plus 7 over 3x to the fourth plus 7x. Oh, I got that? Again, we just showed that the derivative of logarithm is 1 over x. If you have simply x involved, this isn't simply x, this is a function of x. So it's applying the same property. We do 1 over that function, but then by chain rule, we do the derivative of the inside function. The derivative of this is 12x to the third plus 7 times this fraction, so I can just put it in the numerator. On that, anyone? Okay, well, the last one, since we're about basically out of time, I'll just write it up here. It's the same. You go through the same game. You start by letting y equal log base b of x, and you should come up with 1 over x times the log, natural log of b.
Natural log of b.
So you should be able to derive this property here by the same method I did way back over on the right-hand board with the natural log. You should be able to start off with y equals log base b of x, do the inverse of it, and then go from there and get this answer. So there you go. That's the last one we're going to do today. We got them all done. So for homework, you now have 2 sections of homework. You have section 2.4, which covered the chain rule and implicit differentiation. And it's listed on the. Then you have section 5, which covered exponential and logarithm. That's section 4 and 5 of chapter 2. So by Monday, you've got 2 sections of homework. You need to read and study and do homework. You got a lot of time. I want to make sure you have plenty to do to keep you out of trouble. So you're welcome. Thank you, ladies. Y'all have a good weekend. See you on Monday.
No.
Do you remember what you got on part F?
Everyone got that wrong.
And you know I was
I
going
got
to go
part
do
of it
drugs,
right.
but now that
But I was like,
I'm
that's gotta be right.
Exactly.
I'll get the answer. I wrote it down on my copy, so.
Will you send me one?
Yeah, sure.
Oh, you look like you got a question. Just say you can ask.
Just a little bit.
Go ahead, ask the question.
He's asking for the
Just so whenever.
Just
There's a lot of things, but.
negative or positive, or if it was positive, it was negative. So everything would be
Or what?
Every time. Every time.
Be done with Republic.
I
Because
know.
all the derivative rules we learned,
You have one less file.
all these derivative rules deal with simple x.
Just play League, I guess.
So if I had like the whole chain rule just came out, if I said, what if that wasn't simple x? What if it's
I'm
x
just
squared
gonna have to
plus 4
sleep my
raised to
car
the
or
power?
go home.
Well, then I had to do the inside and outside functions separately. That was the chain rule. Well, the same thing here. This is the x. That has a specific property. But if I do each, it's 3x squared plus 4, then you're doing this property and you're doing the changes. Go back and look at this and think about how we started with chain rule there. The rest of these should follow fairly.
It's simple.